2,000-year-old mystery. Look at any modern concrete bridge or parking garage built just 50 years ago. Chances are you'll see cracks, rust, stains, and chunks falling off. Now, look at a Roman harbor like the one in Caesarea. It's been sitting underwater in the Mediterranean for 2,000 years. Not only is it still standing, but scientific analysis shows it's actually gotten stronger over the centuries. How is that possible? We think we're so advanced with our technology, but the Romans had a secret ingredient in their concrete. A secret we're only just beginning to understand. What did they know that we've forgotten? The answer isn't just about thicker walls or luck. It's a chemical recipe lost to history, and it's rewriting what we know about building things to last. The standard story, the usual explanation for why Roman structures have lasted so long, goes something like this. They built things really thick. They didn't use steel reinforcement, and they were mostly building monuments, not the high-stress infrastructure we need today. It's a comforting story because it implies our modern methods are superior. We're just asking more of our materials. But that story falls apart under the slightest scrutiny. For one, many Roman structures, like aqueducts and harbors, were critical infrastructure under immense stress. And the idea that thickness alone explains durability ignores the Pantheon's dome, the largest unreinforced concrete dome in the world. And it's not particularly thick at its apex. It's a masterpiece of engineering, not just brute force. The real puzzle is chemical. Modern concrete and Roman concrete are fundamentally different materials that gain their strength through different processes. Our concrete is based on Portland cement, a recipe perfected in the 19th century. It's designed to set quickly and achieve high strength in a matter of days, which is perfect for our fast-paced construction industry. Roman concrete was different. It was a slower, more complex mixture that continued to chemically evolve for decades, even centuries after it was poured. The Romans weren't just building with rock, they were creating a living material. This difference in philosophy, quick and strong versus slow and durable, is at the heart of the mystery. The standard story is an excuse, a way to dismiss a technology we don't fully comprehend. But when you see a 2,000-year-old pier that's stronger now than the day it was built, you have to admit there's something deeper going on. It's not that the Romans had magic. They had a better understanding of long-term chemistry, one that we are only now rediscovering in laboratories with electron microscopes. The reality is that we may have optimized for the wrong thing, speed over longevity. And the evidence is sitting at the bottom of the sea, quietly defying everything we thought we knew. To really grasp what made Roman concrete so special, we need to understand where it came from and what replaced it. The story doesn't start with the Romans. Civilizations long before them were experimenting with early forms of cement. The ancient Egyptians used gypsum and lime mortars to bind bricks for their pyramids. The Greeks made improvements, but it was the Romans who turned these rudimentary binders into a true building revolution. They didn't just use concrete for foundations. They built with it, creating vast arches, domes, and entire cities out of a material they called opus caementicium. This wasn't just a minor upgrade. It was a transformation in what architecture could be. Before concrete, building large structures meant relying on the compressive strength of stone blocks or columns. With concrete, the Romans could create fluid curved forms. They could span vast distances with arches and vaults. They could build the Pantheon's dome, a structure that would be impressive even with modern engineering. This concrete revolution enabled the rapid expansion of the empire, allowing them to build roads, bridges, and aqueducts at an unprecedented scale. Then the empire fell, and with it, the sophisticated knowledge of how to make high quality concrete largely disappeared. The intricate recipes, the sourcing of specific volcanic ash, the meticulous mixing processes, this organized large scale technical knowledge fragmented in the centuries that followed. Through the Middle Ages, builders reverted to simpler mortars. The grand architectural ambition that concrete allowed was lost. Structures became smaller, relying on timber and stone. The secret of opus caementicium became a legend, a memory of a lost golden age of building. Concrete didn't truly reappear until the 18th century. A key figure was John Smeaton, a British engineer tasked in the 1750s with rebuilding the Eddystone lighthouse, which kept being destroyed by the sea. Through experimentation, Smeaton discovered that limestone containing clay deposits, when heated, produced a hydraulic lime that could set underwater, a property crucial for his lighthouse. He had, in a way, stumbled upon a piece of the Roman secret: the importance of aluminosilicate materials, the clay, in creating a water-resistant binder. His work was a critical step, but it was still a long way from the Roman formula. The real turning point came in the 19th century with the invention of Portland cement. Named because it resembled the high-quality building stone from the Isle of Portland, this was a more industrialized and standardized product. It involved roasting a precise mixture of limestone and clay at very high temperatures, then grinding it into a fine powder. This powder, when mixed with water, would undergo a rapid chemical reaction called hydration, gaining strength quickly. This speed was its greatest selling point. The Industrial Revolution was in full swing. Cities were exploding in size, and there was immense pressure to build fast. Portland cement was perfect for this new, hurried world. It was strong, it was predictable, and it set in days, not years. And so, this new recipe became the global standard, completely overshadowing the slow, patient methods of the Romans. We chose the fast path, and for over a century, we never looked back at the road not taken. Meet the ancient engineers, Vitruvius and Pliny. How do we know anything about this ancient recipe? We have two main guides, an architect and a naturalist. The first is Marcus Vitruvius Polio. Around 30 BCE, he wrote De Architectura, on architecture, a 10-volume encyclopedia that's essentially the only major architectural treatise to survive from antiquity. It's incredibly detailed, covering everything from city planning to aqueducts to the qualifications of a good architect. And crucially, it includes a chapter on building materials. Vitruvius gives us the basic recipe. He describes how to slake quicklime, and he specifically recommends using a type of volcanic ash found in the Bay of Naples near the town of Pozzuoli. He calls it pulvis puteolanus, the dust of Puteoli. He explains that when this ash is mixed with lime and rubble, it creates a mortar that gains strength underwater. This is our primary written source. Our second guide is Gaius Plinius Secundus, better known as Pliny the Elder. A few decades after Vitruvius, Pliny wrote his Natural History, a massive work that aimed to document everything known about the natural world. Pliny doesn't give us a recipe. but he offers crucial observations. He marvels at concrete's properties, describing how it becomes a single stone mass and resists the waves. He also notes the importance of using the highest quality lime and the best pozzolana. Together, Vitruvius and Pliny give us the framework. But here's the catch, and it's a huge one. Their records are incomplete. Vitruvius was writing for other educated Romans, not for future civilizations trying to reverse engineer the technology. He leaves out the precise ratios. He doesn't detail the exact mixing procedure or the curing time. He mentions seawater, but doesn't explain the chemical rationale. It's like getting a famous chef's list of ingredients without any measurements or cooking instructions. This gap in the records is what made the Roman secret so elusive for so long. For centuries, scholars read Vitruvius and thought they understood. They assumed that Roman concrete was just a primitive version of our own. The real breakthrough didn't come from rereading the ancient texts more carefully. It came from putting those texts aside and looking directly at the concrete itself with modern scientific tools. Vitruvius and Pliny gave us the what, but they couldn't give us the why. The why was locked in the microscopic structure of the material, waiting for the right technology to set it free. To appreciate the Roman breakthrough, we first need to be clear about what modern concrete actually is. It seems simple, just a grey, rocky substance. But its strength comes from a precise chemical reaction. The heart of modern concrete is Portland cement. This is the glue. To make it, manufacturers take limestone, which is mostly calcium carbonate, and clay, rich in silica and alumina, and heat them in a kiln to an incredibly high temperature, around 1450 degrees Celsius. This intense heat drives off carbon dioxide from the limestone, leaving behind calcium oxide or quicklime. The quicklime fuses with the silica and alumina in the clay to form small hard nodules called clinker. This clinker is then ground into the fine powder you buy in a bag. When you're ready to build, you mix this cement powder with water and aggregates, sand for fine aggregate, gravel, or crushed stone for coarse aggregate. This is where the magic, or rather, the chemistry, happens. The moment water is added, a process called hydration begins. The compounds in the cement powder dissolve and then reform into new, intricate crystals that interlock with each other and bind the aggregates together. The most important of these crystals is a substance called calcium silicate hydrate, or CSH. Think of CSH as a microscopic, incredibly strong glue that grows out from each grain of cement, weaving through the sand and gravel and locking everything into a solid mass. This reaction generates heat and happens relatively quickly. Within a day, the concrete is hard enough to walk on. Within a week, it has gained most of its strength. And within a month, it's considered fully cured. But this system has inherent weaknesses. The first is brittleness. Concrete is incredibly strong when you try to compress it, but it's very weak when you try to pull it apart, what engineers call low tensile strength. That's why we reinforce it with steel rebar. The steel handles the stretching forces while the concrete handles the squashing forces. It's a brilliant partnership, but it introduces a fatal flaw. The second major weakness is permeability. Concrete is not a solid, impermeable barrier. It's more like a hard sponge full of tiny pores and microcracks that form as the water inside it evaporates during curing. These micro cracks are the material's Achilles heel. Over time, water seeps in through these cracks. In cold climates, that water freezes and expands, widening the cracks. In marine environments, chloride ions from salt water penetrate the concrete. When that salty water eventually reaches the steel rebar, it causes the steel to rust. Rust takes up more volume than the original steel, creating immense internal pressure that cracks the concrete from the inside out, a disease often called concrete cancer. This is why so many of our modern bridges and parking garages have a limited lifespan. Our concrete is designed for rapid strength, not for a centuries long battle against the elements. Its greatest strength is also its greatest vulnerability. The Roman recipe: lime, ash, and seawater. So, if modern concrete is this carefully engineered but fundamentally fragile material, what exactly were the Romans doing differently? Their recipe was deceptively simple. And we know its three core ingredients thanks to Vitruvius. But as we'll see, the magic was in the specific choices they made for each one. First, the binder, lime. The Romans started with limestone, just like we do. They would heat it in a kiln to drive off carbon dioxide, creating quicklime or calcium oxide. This is a brutal caustic powder that gets extremely hot when mixed with water in a process called slaking. So far, this is identical to the first step in making modern Portland cement. But this is where the paths start to diverge dramatically. The second ingredient is where the Romans left us completely behind. Instead of mixing their slaked lime with plain sand, they added a very specific type of volcanic ash. This wasn't just any ash. It came from a particular region in Italy, near the town of Pozzoli. The Romans called it pulvis putiolanus, and we now call it pozzolana. This material is the heart of the secret. Geologically, it's not like the soft powdery ash from a forest fire. It's a gritty, sandy material composed of volcanic glass, crystals, and other minerals. And it's incredibly rich in silica and alumina. The Romans didn't just stumble upon this. They actively sought it out because they observed that structures built with it were far more durable, especially in water. Now for the third ingredient, and it's the one that seems most counterintuitive: seawater. While we use fresh water to mix our concrete, Roman engineers building maritime structures like the harbor at Caesarea would have used seawater straight from the Mediterranean. To a modern engineer, this sounds like a recipe for disaster. We spend enormous effort trying to keep salt away from our concrete because we know it corrodes the steel reinforcement. But the Romans weren't using steel. Their recipe was designed to not just resist seawater, but to actively use it. The chloride ions in the salt water weren't a contaminant. They were a crucial catalyst in a much slower, more complex chemical reaction. This combination, lime, reactive volcanic ash, and seawater, wasn't a primitive version of our concrete. It was a completely different system, one engineered over centuries of trial and error to work in harmony with the environment, not just resist it. They weren't fighting nature. They were recruiting it. Where the magic happens, the Pozzolana reaction. So, what makes this gritty volcanic ash so special? The secret isn't in the lime, it's in the Pozzolana. This isn't just inert filler. Under a microscope, you'd see that it's made of tiny jagged shards of volcanic glass. These shards are packed with silica, which is the same fundamental building block as glass and quartz. But here's the key. This silica is amorphous, meaning its atoms aren't arranged in a rigid, stable crystal structure. They're chaotic and disordered, which makes them highly reactive. When this reactive silica meets the slaked lime and water in the mix, a slow motion chemical dance begins. The lime, which is alkaline, starts to dissolve in the water. The pozzolana particles, with their unstable silica surfaces, act like microscopic sponges, eagerly sucking up the dissolved lime. This triggers a long term reaction called the pozzolanic reaction. Over months and years, the silica from the ash and the calcium from the lime combine to form the same incredibly strong glue found in modern concrete, calcium silicate hydrate, or CST, but there's a crucial difference. In modern concrete, the CSH forms quickly during the initial hydration and then the process mostly stops. In Roman concrete, the pozzolanic reaction is a slow, continuous process. The volcanic ash particles are like a long term chemical battery, slowly releasing reactive silica over decades to create new CSH. This isn't a one and done event. It's an ongoing process of strengthening and densifying the concrete from within. The material isn't just curing, it's maturing, becoming more monolithic and less porous with time. This is the first part of the magic. Roman concrete was designed not for a fast set, but for a long, slow life of getting stronger. While our concrete is essentially finished after 28 days, theirs was just getting started. The modern comparison: two different chemical paths. So we have these two completely different chemical systems. On one side, modern Portland cement, a fast, high energy reaction that creates a strong but brittle and porous material in a matter of weeks. On the other, Roman concrete, a slow, patient process that uses volcanic ash to continuously strengthen and densify the material for centuries. It's not that one is inherently better in all ways, it's that they were designed for completely different priorities. The modern process is a sprint. It's optimized for the economics of construction, to get a building framed and a bridge open to traffic as quickly as possible. The financial model of development rewards speed above almost everything else. The Roman process, by contrast, was a marathon. It was built for the Roman imperial mindset, which was about creating an empire that would last for eternity. They were willing to invest time because they were investing in permanence. Think about the logistics. Without modern machinery, construction projects took years anyway. What was an extra year or two of curing time when you were building a harbor meant to serve for 1,000 years? Their chemical path was slower, but it produced a far more stable and resilient final product. The CSH formed in the pozzolanic reaction is actually a denser, more ordered version of the glue in modern concrete. It's less prone to leaching and chemical breakdown. This is the real trade off we made. We gained incredible speed and the ability to build soaring, delicate structures with reinforced steel. But we lost the built in, long term durability that came from a material designed to evolve with time. Our concrete is essentially chemically inert after a month. Roman concrete was chemically active for its entire life. Water, the great enemy of our structures, was actually a key partner in theirs, continuing to facilitate the strengthening reactions. This fundamental difference in chemical philosophy explains why we see modern concrete decaying after 50 years, while Roman concrete is still gaining strength after 2000. We chose the path of immediate power. They chose the path of endurance, the self-healing phenomenon, cracks that fix themselves. This is where the Roman formula moves from brilliant to almost unbelievable. All concrete, even the Roman kind, develops tiny microcracks over time. It's inevitable. Stress, temperature changes, and simple aging create these microscopic fractures. In modern concrete, these cracks are a death sentence. They're an open invitation for water and chemicals to invade, starting the slow process of decay we talked about. But in Roman concrete, these same cracks trigger the material's secret weapon, self repair. Here's how it works. When seawater seeps into a new microcrack in a Roman structure, it doesn't just sit there, it reactivates the entire chemical system. Remember those unreacted particles of volcanic ash that are still scattered throughout the concrete, acting as a long term chemical reservoir? The water reaches them. It also dissolves a little bit of the lime that's still present. Suddenly, you have all the ingredients for the pozzolanic reaction right there at the crack site: water, lime, and reactive silica. The process starts up again, and new CSH begins to form. But it doesn't just form randomly, it precipitates out of the solution directly inside the crack itself, slowly and methodically, filling the gap from the inside out. It gets even more fascinating. The salt in the seawater plays a direct role. The chloride ions combine with the lime and alumina from the ash to form rare, stable minerals like Friedel's salt and aluminous Tobermorite. These aren't weak fillers, they are dense plate like crystals that lock together, creating a permanent mineralized seal. It's not a patch job, it's the concrete growing new bone to heal a fracture. The system is so effective that researchers who have drilled core samples from Roman maritime structures have found that the cracks are often completely healed, filled with these gleaming white minerals. The concrete isn't just resisting damage, it's actively responding to it. Think of it like an immune system. A microcrack is an injury, and the influx of seawater is the signal that sends the body's repair cells, the unreacted lime and ash, to the site to rebuild. This is the ultimate form of durability. A modern concrete structure requires constant, expensive maintenance to patch and seal cracks before they get worse. A Roman structure, sitting silently on the seafloor, performs its own maintenance for free, forever. It's a closed loop system where the very thing that destroys our buildings, water, is the trigger that continuously restores theirs. The key mineral, Tobermorite and its cousins. So what are these special minerals that act as the concrete's healing agents? For decades, scientists examining Roman concrete samples kept finding traces of a rare crystalline mineral called Tobermorite. In most modern concrete, the glue, the CSH, is amorphous, meaning its atoms are jumbled up. Tobermorite, on the other hand, is a crystalline form of calcium, silicate hydrate. Think of the difference between glass and a diamond. Both are made of carbon-based materials, but one is chaotic and the other has a perfect, strong crystal structure. That's the difference between standard CSH and Tobermorite. The crystalline structure of Tobermorite is incredibly stable, making it far more resistant to chemical attack and physical stress over long periods. But Tobermorite, though, is very difficult to create in a lab, and it's almost never found in modern concrete. Why? Because it typically forms under very specific conditions of high temperature and pressure, like deep underground in geothermal environments. So how on earth did it form in a Roman pier at the bottom of the sea? The answer lies in that third overlooked element, aluminum. The volcanic ash the Romans used wasn't just rich in silica, it also contained a significant amount of alumina. When aluminum atoms are incorporated into the crystal lattice, they form a variant called aluminous Tobermorite. This aluminum seems to be the key that allows the mineral to form at the much lower temperatures and pressures found in a marine environment. This is the true sophistication of the Roman recipe. They weren't just mixing dirt and rocks. They were, through centuries of trial and error, creating the perfect chemical conditions for these ultra stable minerals to grow. The lime provided the calcium, the pozzolana provided the silica, and the crucial aluminum, and the seawater provided the perfect ionic soup to facilitate the slow, long term crystallization. The Roman concrete wasn't a dead material, it was a carefully designed chemical environment that encouraged the growth of a mineral that is naturally suited for longevity. Modern concrete, with its rapid set, doesn't allow time for these complex crystals to form. The process is rushed, and the result is a weaker, more chaotic atomic structure. The Romans, by embracing slowness, allowed their concrete to organize itself into a far more resilient form. The presence of aluminous tobermorite is the smoking gun, the physical evidence that their concrete was fundamentally different from the inside out. It's not just old, it's a material that has spent 2 millennia perfecting its own internal structure, a laboratory breakthrough, analyzing ancient samples. For centuries, the secret of Roman concrete remained just a theory, supported by ancient texts and the obvious durability of the structures themselves. But how do you prove what's happening at a microscopic level inside a 2000-year-old block? You can't just smash the Pantheon to get a sample. The real breakthrough came when scientists finally gained permission to study these ancient relics using tools that Vitruvius couldn't have even imagined. Getting the samples was the first major hurdle. Archaeologists and materials scientists had to work together, carefully extracting small core samples from structures in places where it wouldn't cause damage, like from the hidden foundations of a pier or from blocks already slated for restoration. These samples are priceless, so the analysis had to be incredibly precise and non-destructive wherever possible. The goal was to understand the concrete's history without erasing it. The key was a suite of advanced analytical techniques. Researchers used electron microscopes to peer into the concrete's nanostructure, magnifying it tens of thousands of times. With this, they could see the interlocking crystals of CSH and, crucially, the telltale plates of aluminous tobermorite. They used X-ray diffraction, which is like creating a fingerprint for minerals by seeing how they scatter X-rays. This confirmed the presence of these rare, stable crystals. Another technique, called microdiffraction, allowed them to map the chemical composition inch by inch across a sample, revealing how the recipe might have changed even within a single block. The challenge was immense. They were trying to analyze a chemical process that had been running for 2 millennia. It was like trying to understand the entire history of a forest by looking at a single tree ring. But the moment they saw those crystalline structures, it was a revelation. Here was the physical proof that the Roman concrete was not a static material. The continued presence of unreacted lime and volcanic ash particles showed the chemical battery was still charged, ready to keep healing cracks. The discovery of tobermorite, a mineral that should only form under extreme heat and pressure, proved that the slow ambient temperature pozzolanic reaction was far more powerful than anyone had believed. This wasn't just a different recipe, it was a different class of material, one that had been self-optimizing for centuries under the gentle pressure of the sea. The laboratory evidence transformed the Roman secret from an architectural legend into a scientific fact, opening the door to the possibility that we might one day learn to build this way again. The saltwater secret. Why the sea makes it stronger. This is the part that seems to defy all logic. We spend billions of dollars trying to protect our modern structures from saltwater. We use special coatings, corrosion-resistant rebar, and complex drainage systems, all to keep the chloride ions out. For us, salt is a corrosive contaminant. For Roman concrete, it was a key ingredient. The very thing that destroys our harbors is what made theirs immortal. The secret lies in what those chloride ions do when they meet the Roman mixture. In modern concrete, when salt water seeps in and reaches the steel rebar, it initiates a corrosive reaction. The iron in the steel oxidizes. It rusts. Rust expands, creating immense pressure that cracks the concrete from the inside out in a process we call spalling. It's a death sentence. But Roman concrete had no steel to corrode. Instead, the chloride ions from the seawater were welcomed into the chemical party. They didn't start a destructive process. They started a constructive one. The chloride ions act as a catalyst. They help dissolve more of the lime that's still present in the mixture, making it available for the ongoing pozzolanic reaction. But their most important role is in forming powerful new minerals. The chloride combines with the lime and the alumina from the volcanic ash to create a stable compound called Friedel's salt. This isn't a weak byproduct, it's a dense crystalline mineral that actively helps fill pores and microcracks. Think of it as the concrete growing its own anti-salt armor. At the same time, the salty, alkaline environment is the perfect catalyst for forming the superstar mineral we just talked about, aluminous Tobermorite. The salt water doesn't just facilitate the reaction, it actually helps create a more perfect, more stable crystalline structure within the concrete. So the two materials have a completely opposite relationship with their environment. Modern reinforced concrete is in a constant losing battle against the elements. It's designed to be a barrier, and every crack is a breach in its defenses. Roman concrete is designed to be a collaborator. It doesn't just withstand the sea, it incorporates it. The lapping waves aren't an attack. They're a continuous delivery system, bringing in the moisture and the ions needed to fuel centuries of slow, strengthening reactions. The sea isn't the enemy, it's the lifeblood. This is the ultimate irony. Our modern chemistry, for all its precision, created a material that is fundamentally at odds with the marine environment. Their ancient empirical recipe created a material that thrives in it. They built not just in the sea, but with it. Case study number 1, the Roman port at Caesarea now. All this chemistry is fascinating, but does it actually hold up in the real world? To answer that, we need to look at a structure that was literally designed to fail. Let's travel to the coast of modern-day Israel, to the ancient Roman port of Caesarea Maritima. This wasn't just any harbor. It was a massive, ambitious engineering project commissioned by Herod the Great around 22 BCE. Herod wanted a grand deep water port to rival Athens' Piraeus, and he wanted it built on a coastline that had no natural bays or protective coves. The site was essentially an open beach, facing the full force of the Mediterranean Sea. For a modern engineer, this would be a nightmare scenario. The Romans responded with one of the most audacious construction projects of the ancient world. They built enormous breakwaters right out into the open water, creating a massive artificial harbor. These breakwaters weren't just piles of rock. Their foundations and cores were made of Roman concrete. Huge wooden forms were sunk into the sea, and the lime pozzolana seawater mixture was poured in directly underwater. Think about the confidence that required. They were mixing a recipe that took months to cure, and they were doing it in the one environment guaranteed to test it to its absolute limit from day one: the churning, salty, wave battered Mediterranean. For centuries, the harbor stood as a testament to Roman engineering. But eventually, earthquakes and tsunamis took their toll, and large sections of the breakwaters slipped beneath the waves. And there they sat for nearly 2,000 years. For modern scientists, this sunken ruin became a perfect natural laboratory. They could dive down and extract core samples from concrete that had been continuously submerged in seawater for 2 millennia. What they found was astonishing. The concrete wasn't just intact, it was spectacularly preserved. The outer surfaces were often covered in marine life, but the core material was harder than the rock around it. When they analyzed it, they found the same complex tapestry of minerals we discussed: the long interlocking fibers of CSH and the strong plate-like crystals of aluminous Tobermorite. Most tellingly, they could see the self-healing in action. Cracks that had formed from seismic shifts were completely filled in with white crystalline minerals, the concrete's own repair job. The harbor at Caesarea is the ultimate validation. It's a controlled experiment that has been running for 2,000 years. It proves that the Roman formula wasn't just a theoretical ideal. It was a practical, scalable technology that created structures capable of surviving the worst the environment could throw at them, not for decades, but for millennia. They built for the ages, and at Caesarea, the ages have proven them right. Case study number 2: the Pantheon's unbroken dome. While Caesarea shows us how Roman concrete conquered the sea, the Pantheon in Rome shows us how it conquered the sky. This is perhaps the single most breathtaking example of their mastery. The Pantheon's dome is the world's largest unreinforced concrete dome, and it has been standing for nearly 1,900 years. Just let that sink in. No steel rebar, no internal skeleton, just a massive hemispherical shell of concrete that has defied gravity, earthquakes, and the elements since the reign of Emperor Hadrian. What's even more brilliant is that the Romans didn't use a single, uniform, concrete recipe for the entire structure. They were sophisticated material scientists who tailored the mix for different parts of the building, optimizing for both strength and weight. The heavy foundations and the lower walls are made of a dense, strong concrete, using heavy travertine and brick as aggregate. But as the dome rises and the walls get thinner, the recipe changes. The builders gradually used lighter and lighter materials. They switched from heavy stone to porous volcanic rock like tuff. And then, at the very top of the dome, surrounding the famous oculus, they used the lightest aggregate of all: pumice. Pumice is so light it can float on water. This was a stroke of genius. By lightening the load, as the dome ascended, they dramatically reduced the stress on the lower walls and the massive supporting drum. It's a perfect example of structural optimization long before the invention of computer modeling. They also varied the thickness of the dome itself, making it thinner at the top than at the base where the stresses are greatest. And then there's the coffered ceiling, those recessed square panels you see on the interior. This isn't just decorative. By carving out those sections, they removed a huge amount of weight without significantly compromising the dome's strength. Every single aspect of its design was calculated to achieve the seemingly impossible. So, what can we learn from the Pantheon that's different from the marine concrete at Caesarea? The Pantheon showcases the Roman mastery of structural engineering and their understanding of material properties on a massive scale. It proves their concrete wasn't just durable, it was incredibly versatile. They could engineer its density and weight to create forms that we would still find challenging to build today, even with all our technology. The dome stands as a silent, permanent rebuke to the idea that ancient builders were just lucky. They knew exactly what they were doing, and the Pantheon is their ultimate unfinished argument. The reinforced concrete paradox, strength versus durability. So we have these two incredible Roman achievements, a harbor that heals itself in the sea and a dome that has stood for millennia without any internal support. It paints a picture of near perfect ancient engineering. So, why on earth did we ever abandon this seemingly superior material? The answer lies in a revolutionary 19th century invention that gave us godlike power to build in new ways, but at a terrible hidden cost: steel reinforced concrete. The invention of rebar was a complete game changer. Remember, Roman concrete, for all its durability, had one major weakness we discussed earlier: low tensile strength. It was great at being squeezed, but terrible at being stretched. This limited the shapes and spans they could build. The Pantheon's dome is a marvel, but it's also incredibly heavy and thick. The introduction of steel reinforcement bars solved this problem overnight. Steel has incredibly high tensile strength. By embedding rebar inside wet concrete, we created a new composite material. The concrete handles the compression forces, and the steel handles the tension. This hybrid material was a superpower. It allowed us to build soaring skyscrapers, elegant bridges with impossibly thin decks, and sweeping architectural forms that would have been pure fantasy to the Romans. We could build higher, longer, and with far less material. The economic incentive was irresistible. Construction became faster, cheaper, and more ambitious. But this superpower came with a tragic built-in flaw, a kind of original sin. We created a material with a fatal internal contradiction. The two materials, concrete and steel, have completely different aging processes. We already know that concrete is slightly porous. Water and air will inevitably, eventually seep through. When that moisture reaches the steel rebar, it causes it to rust. And as you know, rust expands. This expansion creates immense internal pressure, cracking the concrete from the inside out in a disease often called concrete cancer. You've seen it, those ugly brown stains and spalling chunks on bridge pillars and parking garages. The very thing that gives modern concrete its strength, the steel, is also the thing that guarantees its eventual decay. The Romans avoided this entirely because their material was monolithic. It was all one chemically consistent mass. Our modern wonder material is a ticking time bomb, a partnership between two materials that are fundamentally at odds over the long term. We traded the eternal endurance of the Romans for the swift, glorious, but ultimately temporary power to reshape the world. The lost knowledge. How a technology disappears. So, how does a technology this effective, a material that could literally last for millennia, simply vanish? It wasn't a single catastrophic event, like the burning of the Library of Alexandria. The loss of Roman concrete knowledge was a slow, quiet fade, driven by a perfect storm of economic, political, and social changes that made the old ways seem obsolete. The Roman Empire didn't just fall, it fragmented. With that fragmentation came the collapse of the large scale state funded infrastructure projects that demanded such durable materials. Emperors building harbors for their navy and aqueducts for their capital cities had an incentive to invest in eternity. The local chieftains and feudal lords who came after were focused on building defensive castles quickly and cheaply. The immense logistical effort required to quarry specific types of volcanic ash from Italy and ship them across the empire became impossible. The knowledge itself was never centralized in a single book. It resided in the hands of the architecti and the master builders, a guild like system of practical knowledge passed down through apprenticeship. As large construction projects vanished, so did the demand for these specialized skills. The masters stopped training apprentices in the old ways because there was no work for them. The intricate, hands on understanding of how to properly slake lime, select the right volcanic ash, and mix it with seawater for a maritime project was replaced by simpler, faster techniques using local materials. It wasn't a case of someone forgetting a password, it was the slow erosion of an entire ecosystem of expertise. The technology didn't disappear overnight, it became a ghost, its principles lingering in a few places for centuries, but never again assembled into the complete, powerful system the Romans had perfected. The world simply moved on, trading the promise of permanence for the necessity of the immediate, the 19th century rediscovery and its limitations. The knowledge was lost for over 1,000 years. But the Industrial Revolution created a new demand for massive, durable structures, and engineers began stumbling toward the Roman secret without even realizing it. The pivotal figure was an English engineer named John Smeaton. In the 1750s, he was tasked with rebuilding the Eddystone Lighthouse, a critical structure that kept getting destroyed by the fierce sea. He needed a mortar that could set underwater. Through pure, painstaking experimentation, he discovered that limestone containing clay impurities, what we'd call a hydraulic lime, would harden even when submerged. He had essentially stumbled upon the basic principle that lime could react with silica and alumina to create a water resistant binder. But Smeaton went a crucial step further. He found that adding a specific type of volcanic ash from Italy dramatically improved the strength and durability of his mortar. He had, completely independently, rediscovered the power of Pozzolana. His lighthouse stood for over a century, a testament to the effectiveness of the Roman principle. For a moment, it looked like the ancient technology might make a full comeback. But then the path diverged. In the early 19th century, a bricklayer named Joseph Aspdin patented Portland cement. He discovered that by burning a precise mixture of limestone and clay at much higher temperatures, he could create a clinker that, when ground into powder, would set faster and achieve a much higher initial strength than Smeaton's hydraulic lime. It was named Portland cement because it resembled the prestigious Portland stone when set. This was the birth of the modern industry, and this is where economics trumped durability. The industrial age was all about speed, scale, and predictability. Portland cement was perfect for this new world. It had a standardized, reliable set time. It achieved high strength within days, not years, allowing for rapid construction that matched the pace of industrial investment and urban expansion. Smeaton's method, relying on specific volcanic ash and a slower cure, was seen as antiquated and inconvenient. The construction industry chose the fast, powerful sprint of Portland cement over the patient, enduring marathon of the Roman formula. They rediscovered the ingredient, but the impatient spirit of the new age meant they never fully embraced the slow, profound chemistry that made it truly eternal. The secret was found and then lost again, this time not to the fall of an empire, but to the rise of a faster one. Modern attempts to replicate the formula. So, if we know the secret ingredients, the lime, the specific volcanic ash, the seawater, why can't we just start making it again? Scientists and engineers have been trying for over a century, but it turns out that replicating 2,000-year-old craftsmanship is a lot harder than it looks. The challenge isn't just the recipe, it's the entire process. From sourcing the materials to having the patience to let nature do its slow, meticulous work. The first major hurdle is finding the right volcanic ash. Not just any ash will do. The Romans had access to incredibly pure deposits from specific volcanic regions in Italy, like Pozzolana, which had the perfect chemical cocktail of reactive silica and alumina. Modern attempts to use ash from other volcanoes often fail because the chemistry is slightly off. The mineral composition, the particle size, even the specific crystalline structure of the ash can throw the entire reaction out of balance. You can't just substitute fly ash from a coal plant and expect the same result. The magic is in the specific geological history of the Italian volcanoes. Even when researchers get the right ash, they face the problem of mixing. The Romans mixed by hand, often directly in wooden forms in the sea. This wasn't a precise laboratory grade process, it was messy. And that messiness might have been part of the success, allowing for a more varied and robust chemical environment. Modern industrial mixing aims for perfect homogeneity, which might actually work against the formation of the complex, interlocking crystal structures that give Roman concrete its strength. Then there's the time factor, which is perhaps the biggest economic barrier. Modern construction operates on timelines of months, not decades. A developer financing a new seawall can't wait 5 years for the concrete to finish its initial curing process before the project can be considered complete and start generating revenue. Our entire system of contracts, insurance, and financing is built around the rapid strength gain of Portland cement. A material that takes years to reach its full potential is, in today's terms, commercially unviable for almost all applications. Scientists in labs can create small samples that, after years of curing, show promising similarities to the Roman material. But scaling that up to a harbor breakwater or a building foundation, and then convincing someone to wait a lifetime to see the final result, is a problem that science alone can't solve. It's a clash between the timeless logic of chemistry and the relentless ticking of the financial clock. We have the knowledge, but we may have lost the societal patience required to use it. Geopolymer cement, A modern cousin. If we can't perfectly replicate the Roman process, could we at least create a modern material that captures its spirit? That's the promise of geopolymer cement, a fascinating class of materials developed in the late 20th century. In many ways, geopolymer cement feels like the Roman formula's brilliant, high tech cousin. It completely bypasses the high temperature process of making Portland cement. Instead, it's made by taking an aluminosilicate source material, like fly ash from coal plants or slag from steel production, and activating it with a highly alkaline solution. This chemical process is strikingly similar to what happens in Roman concrete. You have a silica and alumina rich powder, the Roman pozzolana, or modern fly ash, reacting with an alkaline activator, the Roman lime or a modern chemical solution, to form a strong, stable binder. The resulting material, like its ancient relative, is highly resistant to chemicals, heat, and doesn't suffer from the same corrosive issues as steel reinforced concrete. It even has a much lower carbon footprint since it doesn't require roasting limestone at extreme temperatures. For a moment, it seems like we've finally caught up to the Romans, using our own industrial byproducts. But here's the catch, and it's a significant one. Geopolymer cement isn't a perfect replica. Its chemistry, while similar, is different. The alkaline activator used is typically a harsh chemical, like sodium hydroxide or potassium silicate, not the simpler slaked lime the Romans used. This makes the mixing process more hazardous and complex. More importantly, the long-term durability of geopolymers is still being studied. We know Roman concrete lasts 2000 years. We're still waiting to see how geopolymers perform over a century. The real distinction, though, lies in the self-healing property. The Roman secret wasn't just creating a strong binder, it was creating a chemical system with a long-term reserve of reactive ingredients. Most modern geopolymers are designed to react completely and quickly, leaving little behind for future repairs. They are a fantastic, durable material, but they haven't yet captured the living, self-maintaining character of the ancient recipe. They are a parallel evolution, a brilliant, modern solution inspired by an ancient principle, but not yet a true rebirth of the lost technology. It shows we're thinking in the right direction, even if the final destination remains just out of reach. The environmental angle, a greener concrete. This brings us to one of the most compelling reasons to look back at this ancient technology: the staggering environmental cost of our modern alternative. The production of Portland cement is a massive contributor to global CO2 emissions. In fact, it's responsible for about 8% of the entire world's carbon dioxide output. That's more than the entire aviation industry. The reason is simple chemistry. To make Portland cement, you have to heat limestone, which is mostly calcium carbonate, to temperatures over 1400 degrees Celsius. This process, called calcination, drives off carbon dioxide, turning the limestone into quicklime. So you're burning massive amounts of fossil fuels to create that intense heat. And you're also directly releasing CO2 that was locked inside the rock itself. It's a double whammy of pollution. Now, let's compare that to the Roman method. Their process started with limestone too. They had to heat it to create quicklime. But the critical difference is the temperature. Roman lime kilns operated at much lower temperatures, around 900 degrees Celsius. That's a significant energy saving right there. But the real environmental advantage comes from the recipe itself. Because Roman concrete uses much less lime overall. The bulk of the binder isn't just lime. It's the volcanic ash, which is a natural pozzolan. You don't have to burn that, you just dig it up. So the carbon footprint of the Roman recipe is inherently lower because it replaces a significant portion of the energy intensive cement with a natural, unprocessed material. This has led to a modern movement to use supplementary cementitious materials in concrete. The most common one is fly ash, which is the fine powder left over from burning coal. It's a pozzolan, much like the Roman volcanic ash. By replacing a percentage of Portland cement with fly ash, we can reduce the CO2 footprint of the concrete. It's a great idea, and it's a direct nod to the Roman principle. But it's still just a partial fix. We're still relying on the high heat Portland cement process as the base. The Roman method suggests a more radical path. What if we could create a high performance concrete that uses little to no Portland cement at all? What if we could build with a material whose production is closer to the lower energy Roman model? The environmental potential is enormous. It's not just about making a concrete that lasts longer. It's about making a concrete whose very creation is less harmful to the planet. The Romans, by accident or by design, built with a material that was sustainable in a way we are only now, 2000 years later, desperately trying to replicate. Their ancient secret might hold a key to solving one of our most pressing modern problems. The economic hurdle. Why we don't build like Romans. If this material is so durable and potentially greener, why isn't it being used to build everything from our highways to our homes? The answer lies in a fundamental conflict between the logic of chemistry and the logic of modern economics. Our entire construction industry is built on a financial model that prioritizes speed and low upfront cost above all else. Roman concrete fails this test spectacularly. Think about how a modern construction project is financed. A developer gets a loan to build an apartment building or a bridge. That loan accrues interest every single day. The faster the project is completed and starts generating revenue through rent or tolls, the more profitable it is. Construction timelines are measured in months and delays cost millions. Now, imagine telling that developer that the concrete for the foundation won't reach its full strength for 5 years. The project would be financially impossible. The slow, patient curing process that gives Roman concrete its eternal life is completely incompatible with the fast paced, debt financed world of modern development. Then there's the issue of standardization and liability. The modern construction industry relies on materials with predictable, certified performance. Engineers can specify a certain grade of Portland cement and know exactly how strong it will be after 28 days. This predictability is crucial for calculating loads, getting building permits, and most importantly, for insurance. Insurance companies need to know the risks. How would you insure a building made with a material whose strength continues to evolve for decades? The long term benefit is a theoretical gain for future generations, but the short term liability falls on the builder and owner today. It's a risk our system is not set up to take. Finally, there's the simple matter of material cost and logistics. Sourcing the specific type of volcanic ash the Romans used isn't like ordering gravel. The best deposits are in Italy. Shipping that material globally would be incredibly expensive, both financially and environmentally. While we can use local pozzolans like fly ash, as we discussed, getting the exact chemical balance right for the self healing properties is still a challenge. The Roman method was optimized for a specific geography with local materials. Adapting it globally requires a level of customization that our mass production economy resists. We chose a path of uniformity and speed 2 centuries ago, and the economic inertia of that decision is now a concrete wall, much harder to break than the material itself. We're trapped in a system that values immediate return on investment over intergenerational legacy. And until that calculus changes, the Roman secret will remain a fascinating laboratory experiment rather than a foundation for our future. Lessons from history. Engineering for the long term. This brings us to perhaps the most profound lesson the Romans have to teach us. And it has nothing to do with chemistry and everything to do with mindset. The fundamental difference between their concrete and ours isn't just in the ingredients, it's in the timeline they were building for. The Roman worldview was fundamentally intergenerational. An emperor like Augustus or Hadrian wasn't just building for their own reign, they were building monuments to cement their legacy for eternity. They were making a statement to the gods, to their rivals, and to citizens 1,000 years in the future. Rome is permanent. This mindset infused their engineering. They invested the extra labor, sought out the specific materials, and accepted the slower curing times because the payoff wasn't a quarterly earnings report. It was a civilization that would outlast them. Contrast that with our modern approach. Our infrastructure is often built with a designed lifespan. A bridge might be engineered to last 50 or 100 years. We operate on a model of planned or at least accepted obsolescence. We build with the understanding that future generations will have to repair, replace, or demolish what we've created. This isn't necessarily due to malice or short-sightedness. It's a reflection of our faster-paced, economically driven world. But it creates a hidden, accumulating cost. The billions we save today by using faster, cheaper concrete are simply deferred as a bill that our children and grandchildren will have to pay, both financially and environmentally, when these structures inevitably fail and need to be torn down and rebuilt. The Roman method forces us to ask a difficult question. What is the true cost of a building? Is it just the initial price tag, or is it the total cost over its entire lifetime, including maintenance, repairs, and eventual demolition? When you factor in the endless cycle of repaving roads, repairing bridges, and rebuilding seawalls, our cheap concrete starts to look incredibly expensive. The Romans paid a higher upfront cost for a material that would essentially maintain itself for millennia. We pay a lower upfront cost for a material that becomes a recurring financial and environmental liability. It's the difference between buying a single, well-crafted tool that lasts a lifetime and buying a disposable one you have to replace every year. Over a long enough timeline, the cheap option becomes the most expensive one. So the real secret we've lost might not be a chemical formula, but a philosophy. It's the value of patience. It's the willingness to make a greater investment today for a payoff that you yourself may never fully enjoy. The Pantheon and the harbor at Caesarea are gifts from the past to the present. They are a testament to a culture that believed in leaving something behind that was better than what they found. As we face our own challenges with crumbling infrastructure and climate change, perhaps the most valuable thing we can rediscover is not just how they mixed their concrete, but why they bothered to make it so perfect in the first place. It's a lesson in building not just for ourselves, but for the ages. The role of trial and error, centuries of refinement. So how did the Romans arrive at this near perfect recipe? They didn't have electron microscopes or X-ray diffraction machines. They didn't understand the molecular structure of Tobermorite. Their process was one of relentless, patient, and incredibly long term trial and error. This wasn't a technology invented by a single genius in a lab. It was refined over centuries by countless anonymous engineers, masons, and builders who learned what worked and, more importantly, what didn't through hard practical experience. We can actually see this evolution etched into the ruins of the empire itself. Archaeologists and material scientists who core sample different structures from different time periods have found that the recipe wasn't static. A seawall built in the 2nd century BCE uses a different mix of ash and lime than a bridge built in the 2nd century CE. The Romans were constantly tweaking the formula. They experimented with different volcanic deposits from all over Italy, learning that the reddish ash from Pozzoli was superior to the grey ash from another region. They adjusted the ratio of lime to ash, figuring out that more ash made a better maritime concrete, while a different mix was better for foundations on land. This was a massive distributed R&D project that spanned generations. A master builder in Gaul would learn a technique that worked for the local materials and climate. And that knowledge would slowly filter back along the trade routes. They learned through catastrophic failures too. We talked about how some Roman concrete did fail. And you can bet that when a new harbor's breakwater collapsed in a storm, the engineers of the time took note. They would have examined the rubble, seen where the mix was too weak or the aggregates were wrong, and adjusted their methods for the next project. This is the real secret behind their success. A culture of empirical engineering that valued observation and incremental improvement over theory. They didn't need to understand the why at a molecular level. They just needed to know that this specific mix from this quarry mixed with this amount of seawater and left to cure for this long produced a rock that would last forever. They were masters of the how, and they passed that hard-won knowledge down through the centuries. One successful and failed construction project at a time. The microbiome of concrete, a new frontier. While the Romans achieved self-healing through chemistry, modern scientists are exploring an entirely different path to the same goal, one that draws inspiration from biology. Welcome to the strange new world of self-healing concrete that uses bacteria. This isn't science fiction, it's a real field of research, and it creates a fascinating parallel to the ancient Roman process. The idea is surprisingly simple. Scientists mix specific strains of bacteria, along with a food source for them, into the concrete while it's being made. These bacteria are chosen because they can lie dormant for years, even decades, surviving in the harsh, dry, alkaline environment inside the concrete. They're essentially in a state of suspended animation. But when a crack forms and water seeps in, it wakes the bacteria up. As they become active, they consume their food source, often calcium lactate, and as a byproduct of their metabolism, they precipitate calcite, a form of limestone. This calcite gradually fills the crack, sealing it shut from the inside. It's like giving the concrete its own immune system. Now, let's compare this to the Roman method. The goal is identical: automatic repair of microcracks to prevent bigger problems. But the mechanisms are worlds apart. The Romans relied on a passive chemical process. The ingredients for repair, the leftover non-reacted lime and the reactive volcanic glass, were already in the mix. Water wasn't an enemy. It was the catalyst that triggered the healing reaction. The modern bacterial method is more like introducing a tiny living repair crew. It's an active biological system. Each approach has its pros and cons. The bacterial method is a brilliant piece of bioengineering, but it introduces living element into an inert material, which raises questions about long-term viability. What happens when the bacteria's food supply runs out? The Roman method is purely chemical and mineralogical. Its healing potential is limited only by the remaining reactive material in the concrete, which, as we've seen, can last for centuries. It's a closed, stable system. The most exciting possibility, however, is a hybrid approach. What if we could combine the rapid, targeted repair of bacteria with the long term chemical stability of a Roman inspired pozzolanic mix? We could create a concrete that can handle immediate damage with biology and ensure century long durability with chemistry. It's a powerful example of how looking back at ancient wisdom can inspire truly futuristic solutions, blending the best of the old world and the new to build a more resilient future. Analyzing the harbor of Portus, Rome's main port. While the harbor at Caesarea is a stunning example of Roman marine concrete, it was essentially a massive standalone project. To truly understand how integrated this technology was into the Roman world, we have to look at Portus, the main maritime hub of the empire itself. Located a few miles from Rome at the mouth of the Tiber River, Portus was the central nervous system of Roman trade. Everything from Egyptian grain to Spanish olive oil and British tin flowed through this massive artificial harbor. It was the logistical engine of an empire, and it was built almost entirely using the concrete we've been discussing. The scale was staggering. The main basin, begun by Emperor Claudius, was a huge hexagonal harbor covering over 200 acres. It was protected by massive concrete breakwaters that stretched far out into the Mediterranean Sea. What's incredible for archaeologists is that much of this infrastructure now lies underwater, preserved in a marine environment rather than being torn down for new construction. This gives scientists a nearly perfect laboratory. By taking core samples from these submerged breakwaters, they can analyze the concrete that has been bathed in seawater for 2000 years, exactly as the Roman engineers intended. The findings at Portus have revealed another layer of sophistication. The concrete here isn't uniform. The Romans weren't just dumping the same mix everywhere. By studying the stratigraphy, the different layers within a single concrete structure, researchers can see how the builders adjusted their technique. The outer layers of the breakwaters, which faced the constant pounding of the waves, used a denser, stronger mix with a specific type of coarse aggregate. Further inside the structure, where the pressure was less intense, they might have used a slightly different recipe, perhaps to save on materials or labor. This shows an incredible understanding of material science. They weren't just making a monolithic block. They were engineering a composite structure, optimizing the material for its specific job within the larger whole. It's the kind of smart, efficient design you'd expect from a modern engineering firm, not an ancient civilization. Analysis of these cores has also provided crucial evidence for the long-term chemical reactions we talked about earlier. The concrete from the heart of the Portus breakwaters shows a perfect crystalline structure with the telltale signs of Tobermorite and other stable minerals. But the real proof is at the edges, where the concrete has been exposed to the seawater for millennia. Instead of being eroded or degraded, the surface layers show a kind of rind, a harder, more crystallized zone where the ongoing pozzolanic reaction has actually strengthened the material against the elements. The harbor of Portus isn't just a ruin, it's a living document. It's a 2,000-year-long experiment that is still running, proving that the Roman method wasn't just a clever trick. It was a profoundly durable system for building on a colossal scale. By studying its silent, submerged walls, we're not just learning about the past, we're reading a masterclass in engineering for the future, the volcanic hotspot. Why Italy had the perfect ingredients. So we know the Romans used a special volcanic ash. But why them? Why didn't the Egyptians or the Greeks develop this incredible material? The answer is written in the very ground beneath their feet. The Italian peninsula is one of the most volcanically active regions on Earth. And the Romans had the incredible fortune of building their civilization right on top of a geological gold mine. They weren't just lucky, they were perfectly positioned. Think about the geography. The Romans were surrounded by volcanoes. To the south, Mount Vesuvius, whose eruption would later bury Pompeii. A little further south, the Phlegraean Fields, a vast supervolcanic caldera near modern-day Naples. And this area, specifically the town of Pozzuoli, gave its name to the magic ingredient, pozzolana. This wasn't just any old volcanic dirt. The ash from this region is incredibly rich in reactive silica and alumina, the very chemicals that, when mixed with lime, create that strong, stable binder. The volcanic activity in Italy is part of the complex collision between the African and Eurasian tectonic plates, which creates a specific type of explosive volcano. These eruptions produce a fine, glassy ash that is perfect for the pozzolanic reaction. Other civilizations had access to volcanic materials, but the specific chemistry of the Italian deposits was, quite simply, the best in the ancient world. And the Romans knew it. They weren't just using whatever was locally available. They actively sought out the best sources. Pozzolana, from the Bay of Naples, became a valuable trade commodity, shipped all across the Mediterranean to major construction sites. When they built the harbor at Caesarea in Judea, they didn't use local sand. They imported the specific ash from Italy because they knew it was superior. This tells us something important. The Romans had developed a sophisticated understanding of material quality. They could empirically test different deposits and recognize that the reddish, gritty ash from Pozzuoli produced a stronger, more durable concrete than other varieties. Their empire gave them access to diverse resources, but their engineering wisdom led them to consistently choose the best one. Italy's unique geology provided the perfect ingredient, but Roman ingenuity and logistical power are what turned that local advantage into an empire-wide building standard. It was a perfect storm of having the right resources and the intelligence to exploit them fully. Without that specific volcanic landscape, the secret of Roman concrete might never have been discovered. The recipe variations, not one secret, but many so far. We've been talking about Roman concrete as if it were a single magical recipe. But here's where the story gets even more impressive. The Romans weren't using one secret formula, they had a whole cookbook. They were master material scientists who understood that you needed a different mix for a harbor wall than you did for the dome of a temple or the foundation of an aqueduct. The real secret wasn't a single set of instructions. It was a sophisticated system of material engineering tailored to the specific job at hand. Think about it like baking. You wouldn't use the same recipe for a dense, crusty bread as you would for a light, fluffy cake. The Romans thought the same way about their concrete. For massive marine structures like the breakwaters at Portos, they used a specific heavy-duty mix. The aggregates, the rocky chunks mixed in, were often chunks of tuff, a volcanic rock itself, or other dense stones. This created a concrete that was incredibly strong and resistant to the relentless pounding of ocean waves. But then look at the Pantheon's dome. At its very top, the concrete is incredibly light. How did they manage that? They changed the aggregate. Instead of heavy stone, they used lightweight materials like pumice, a volcanic rock filled with air bubbles. This brilliant adjustment reduced the immense weight and stress on the structure, allowing them to build that magnificent unsupported dome. They were literally engineering the weight and strength of the material as they built upwards. This customization wasn't just for grand monuments either. As the empire expanded, Roman engineers had to adapt to local conditions. If you were building a fort in a province like Britain, you couldn't always ship tons of premium Italian pozzolana across the continent. So they got creative. They would test local materials. In some places, they found that crushed pottery or brick dust, materials rich in reactive silica and alumina, could act as a substitute for volcanic ash. The resulting concrete might not have been quite as perfect as the mix used in the heart of Rome, but it was still vastly superior to anything else available at the time. This shows a flexible, practical intelligence. They understood the core principle, the reaction between lime and a pozzolan, and they applied it with whatever high-quality materials they had on hand. This wasn't a rigid dogma. It was a living technology, constantly being refined and adapted. It proves that their greatest achievement wasn't just discovering a great recipe, but developing a deep, systemic understanding of how materials behave, an understanding that allowed them to build an empire that literally stood the test of time. The maintenance myth. Did Romans actually maintain their concrete? It's tempting to imagine Roman structures springing up perfectly and then standing untouched for 2 millennia, a testament to a set it and forget it building philosophy. But that's a romantic exaggeration. The truth is more practical, and in some ways even more impressive. Roman concrete wasn't magic. It was just incredibly well designed. And good design doesn't eliminate maintenance. It just changes its nature. The evidence is right there in the ruins. If you look closely at structures like the Colosseum or the aqueducts, you can find clear signs of repairs. You'll see patches where sections of stone or concrete were replaced, or where metal clamps were added to stabilize cracked blocks. Roman engineers and the officials who funded them absolutely understood that structures needed upkeep. The key difference lies in what needed maintaining. In a modern steel-reinforced concrete building, a tiny crack can be a death sentence. If water reaches the rebar, it starts to rust, and the rust expands with immense force, cracking the concrete from the inside out in a process called concrete cancer. Fixing this isn't a simple patch job. It often requires demolishing and replacing entire sections. Roman concrete, being unreinforced, didn't have this fatal flaw. Its maintenance was almost entirely superficial. The core of the structure, the concrete itself, was designed to be stable and, as we've seen, even self-repairing on a microscopic level. The maintenance they performed was typically on the non-structural elements, the marble veneers that clad the walls, the lead seals in the aqueducts, the wooden beams in the roofs, or the decorative stucco. The underlying concrete skeleton was so robust that it could survive for centuries even if its decorative skin was stripped away by looters or damaged by earthquakes. They maintained the building's function and appearance, but they rarely had to fix the building's fundamental structure. This distinction is crucial. The Roman achievement wasn't creating a maintenance free material, it was creating a material whose core integrity was so resilient that it reduced maintenance from a structural emergency to a matter of cosmetic upkeep. They built a backbone so strong that it could carry the weight of history even when everything else fell away. They understood that you care for a great building, you tend to it, but you shouldn't have to constantly save it from collapse. Their concrete gave them that luxury, allowing their monuments to endure not through neglect, but through brilliant, forgiving design. Modern applications where Roman style concrete makes sense today. So, if it's not practical to rebuild the entire modern world with Roman concrete, where does this ancient technology actually make sense today? The answer lies in projects where the incredible long term durability and low maintenance outweigh the higher initial cost and slower construction time. These are niche applications, but they're incredibly important ones. The most obvious use is in marine environments, exactly where the Romans used it best. Think about seawalls, breakwaters, or offshore wind turbine foundations. These structures are constantly battered by salt water, which is absolute hell on modern reinforced concrete. The steel rebar corrodes, the concrete spalls, and they require constant, expensive repairs. Using a Roman inspired, unreinforced pozzolanic concrete could be a game changer here. It would be designed to last for centuries with minimal upkeep, and it would actually get stronger in the seawater instead of weaker. The initial investment would be higher, but the lifetime cost would be dramatically lower. It's the perfect solution for protecting our coastlines from erosion and rising sea levels in a truly permanent way. Another critical application is in the containment of hazardous materials, particularly nuclear waste. This is a problem that requires thinking on a Roman timescale. We need storage solutions that are guaranteed to remain intact and isolated for thousands of years, far beyond the lifespan of any corporation or government. Modern materials simply aren't certified for that kind of longevity. A concrete based on the Roman recipe, which has already proven its stability over millennia, offers a promising avenue. Its mineralogical stability and self healing properties could provide a robust barrier that passively maintains its integrity, reducing the risk of catastrophic failure for generations to come. It's a modern problem that demands an ancient kind of certainty. Finally, there's the field of architectural conservation. What better material to use when restoring a 2000-year-old Roman structure than the original material itself? Using modern Portland cement to patch an ancient aqueduct is a terrible idea. It's chemically incompatible and will likely cause more damage in the long run. By relearning and using the original Roman recipes, conservators can make repairs that are true to the original construction and will age along with it. This isn't just about building new things, it's about honoring and preserving the old, using the very same wisdom that created them. In these specialized fields, the Roman secret isn't a historical curiosity. It's the most advanced and appropriate technology for the job. The University of Utah breakthrough, cracking the code. For centuries, the secret of Roman concrete was locked inside the stone itself, a mystery that old texts couldn't fully explain. The real turning point, the moment this went from Historical curiosity to serious science came from a dedicated research team at the University of Utah, led by geologist Professor Marie Jackson. Her work didn't just look at the concrete, she looked into it, using tools the Roman engineers could never have imagined to finally understand what was happening at a microscopic level. The challenge was immense. You can't just take a sledgehammer to the Pantheon to get a sample. Jackson and her international colleagues had to get special permission to take tiny core samples from ancient Roman structures, including those ancient marine breakwaters. These cores are like geological biopsies, giving them a cross section of the material's history. Then came the high tech forensics. They used powerful electron microscopes to see the intricate crystalline structure and X ray diffraction to identify the specific minerals present. It was like being able to read the concrete's DNA. The breakthrough came when they zoomed in far enough to see the stunningly complex microstructure. They didn't just find the expected calcium silicate hydrate, the standard glue of all concrete. They found something more rare and more stable. The crystalline minerals, Tobermorite and philipsite, growing within the matrix like a reinforcing scaffold. The real aha moment was understanding how these crystals formed. They weren't there from the beginning. The team realized that as seawater slowly seeped through the concrete over centuries, it was dissolving components of the volcanic ash, essentially leaching out more silica. This silica then reacted with the leftover lime in the concrete, slowly, patiently, growing these strong plate-like crystals that interlaced and blocked the microcracks. The concrete wasn't just sitting there, it was continuously remodeling and strengthening itself from the inside out, using the environment as a partner in the process. Inspired by this discovery, Jackson's team didn't stop at just understanding the past. They tried to recreate it. They partnered with engineers to create a modern version of Roman concrete, using volcanic ash from the western United States. They mixed it with lime and cured it in seawater tanks, carefully monitoring the chemical changes. The goal wasn't necessarily to replace all modern concrete overnight, but to prove that the process could be replicated and understood with modern scientific rigor. Her papers, published in prestigious journals, sparked a renaissance in the field, moving the discussion from wasn't Roman concrete neat to how can we use these principles to build a more durable future. This scientific validation was the key that unlocked the ancient secret, transforming legendary durability into a reproducible, modern engineering goal, the time factor. Patience as an ingredient, Professor Jackson's research highlights a critical ingredient in the Roman recipe that we can't buy or manufacture: patience. Our modern concrete is designed for speed. It's a race against the clock, aiming for high strength in just 28 days so construction can race ahead. This speed comes at a cost, creating a more brittle, less stable internal structure. The Roman process was the complete opposite. It was a slow, patient chemical symphony that played out over decades. The initial setting was relatively quick, but the real magic, the crystallization of minerals like Tobermorite, happened incredibly slowly as water seeped through the material over years and even centuries. This wasn't a flaw, it was the design. The concrete was engineered to use time as a tool for strengthening. This creates a fundamental conflict with our modern world. Our entire economy and construction industry are built on the premise of speed. A faster build means lower interest payments on loans and a quicker return on investment. We simply don't have the economic or social patience to wait years for a building's foundation to reach its full strength. we've prioritized immediate utility over long term resilience. The Roman method forces us to confront a difficult question. Have we sacrificed permanence for the sake of convenience? Their concrete is a testament to an intergenerational mindset where builders invested in a future they would never see, trusting that their work would serve generations to come. We built for our lifetime, they built for the ages. This difference in perspective is as important as the difference between lime and Portland cement. It's a lesson in valuing the long game, in understanding that some of the strongest bonds, whether in relationships or in concrete, are the ones that take the most time to form. The role of aluminum, the overlooked element. We've talked a lot about silica and lime, but there's a third, often overlooked player in this chemical symphony that turned out to be just as important: aluminum. When scientists like Marie Jackson analyzed the Roman samples, they didn't just find the expected calcium silicate hydrate. They found something even better: aluminous tobermorite. That aluminous part is the key. It turns out the volcanic ash the Romans favored wasn't just rich in silica, it was also packed with alumina. And this aluminum didn't just get swept along for the ride, it became a fundamental part of the concrete's molecular backbone. Here's why that matters. In the complex gel-like matrix of concrete, aluminum ions can step in and replace some of the silicon ions. This might sound like a tiny, insignificant swap, but on a molecular level, it's a game changer. This substitution creates a much more stable and ordered crystalline structure. It's the difference between a haphazard pile of bricks and a carefully laid brick wall. The aluminum acts like a reinforcing agent within the calcium silicate hydrate, making it less susceptible to chemical attack and physical degradation. It's this aluminous tobermorite that gives the Roman concrete its legendary resistance, especially against the corrosive power of seawater. Modern Portland cement mixtures can sometimes form a similar mineral, but it's usually unstable and breaks down easily. The Romans, completely by accident and through centuries of trial and error, stumbled upon the perfect chemical conditions to form a stable version that lasts for millennia. The genius of the Roman system was that the aluminum was baked right into their primary ingredient. They weren't adding a separate chemical. They were simply using a volcanic ash that naturally contained the perfect ratio of silica to alumina. This is another reason why the specific ash from Pozzoli was so prized. Its unique geochemical signature provided the ideal raw materials for a reaction the Romans couldn't even see, creating a durable, self-healing stone that we are only now beginning to fully understand. The aluminum was their secret weapon, an invisible ingredient that gave their concrete its incredible strength and longevity. Failure analysis. When Roman concrete did fail, it would be a mistake, though, to imagine Roman concrete was invincible. To truly understand its strengths, we also have to look at its weaknesses. For every Pantheon that stands triumphant, there's a ruin that tells a story of failure. And these failures are just as instructive as the successes. They show us the limits of the material and, more importantly, reveal the incredible engineering judgment the Romans developed through hard experience. One of the most common points of failure wasn't the concrete itself, but what lay beneath it. The Romans were brilliant engineers, but their understanding of soil mechanics was primitive by today's standards. There are examples of massive structures, like sections of aqueducts or large buildings, that collapsed because their foundations settled unevenly or gave way entirely. The concrete might have been perfectly mixed, but if the ground it sat on shifted, the entire structure was doomed. Earthquakes were another major threat. While the unreinforced concrete had a degree of flexibility, a severe seismic event could generate forces that simply overwhelmed the material's tensile strength, causing it to crack and crumble. Perhaps the most fascinating failures are the ones that reveal flawed recipes. Archaeologists have found instances where the mix was clearly wrong. Maybe the lime wasn't properly slaked, leaving behind unstable chunks that would later expand and crack. Or perhaps builders in a remote province, without access to good pozzolana, used a poor substitute that didn't react properly, resulting in a weak, crumbly concrete that quickly deteriorated. These aren't signs of a failed technology. They are evidence of a learning process. When a structure failed, you can bet Roman engineers would have examined the rubble. They would have seen the poorly slaked lime or the inferior aggregate and added that knowledge to their collective wisdom. A failure in goal might have led to an improved standard for lime preparation across the entire empire. This process of learning from disaster highlights a key difference between ancient and modern engineering. Today, we rely heavily on theoretical models and computer simulations to predict failure. The Romans relied on empirical evidence, on seeing what actually happened when a wall fell down. This hands-on, trial and error approach, while slower, gave them a profound, practical understanding of their material's behavior. They learned to respect its limits. They understood that even the best concrete couldn't overcome a bad foundation or a massive earthquake. By studying their failures, we see that their genius wasn't just in the recipe. It was in their growing ability to understand the entire system, the soil, the design, the materials, and the forces of nature, and to build in a way that worked in harmony with it, not against it. Their concrete was a powerful tool, but it was the wisdom of the engineers wielding it that truly built an empire. The global distribution, Roman concrete beyond Italy. So if the perfect ingredients were in Italy, how did the Romans manage to build such durable structures across their entire empire? From the rainy hills of Britain to the deserts of Syria, the answer reveals another layer of their brilliance. They weren't just exporting a single recipe, they were exporting a system of knowledge and a remarkable ability to adapt. The presence of high-quality Roman concrete, far from the volcanic fields of Italy, is proof of their sophisticated logistics and their deep practical understanding of material science. In places crucial to imperial power, they went to incredible lengths to bring the best materials with them. For monumental projects like a legionary fortress or a provincial capital, they would actually ship the key ingredient, the high-quality pozzolana, from Italy itself. The harbor at Caesarea is the classic example, but archaeologists have found evidence of imported Italian volcanic ash at sites across the Mediterranean. This was a massive undertaking, a testament to how highly they valued the performance of this specific material. It was worth the immense cost and effort to ensure that the foundations of their power were literally unshakable. But the empire was vast, and you can't ship volcanic ash to every single bridge, aqueduct, and villa. This is where Roman engineering truly shines. When local materials had to be used, the engineers became innovators. They conducted what we'd now call field testing. They would experiment with locally available materials that had similar properties to pozzolana. In regions without recent volcanoes, they discovered fantastic alternatives. Crushed terracotta, broken pottery, and brick dust turned out to be an excellent substitute. When fired in a kiln, clay becomes rich in reactive silica and alumina, mimicking the chemistry of volcanic ash. In parts of Germany and Britain, they even used certain types of volcanic rock that, while not as perfect as the ash from Pozzolani, could still produce a strong hydraulic concrete when crushed. This adaptability shows that the Romans had moved beyond simply following a recipe. They understood the fundamental chemical principle. You need a source of reactive silica to combine with lime. Whether that silica came from a volcano in Italy or a pottery shard in Gaul was, to some extent, secondary. The quality control across this vast network was impressive. While a small rural bathhouse might have a rougher, locally sourced mix, the core structural elements of important provincial buildings show a consistent standard of excellence. This combination of centralized knowledge and local adaptation was key to their success. It allowed them to stamp their architectural identity across three continents, building a unified empire not with a rigid formula, but with a flexible, intelligent system that could thrive anywhere on Earth. Their concrete was more than a material. It was a language of power and permanence that they learned to speak in every corner of their world. The cultural context, concrete and Roman identity. But this story is about more than just chemistry and engineering. To understand why the Romans poured so much ingenuity into this material, we have to understand what concrete meant to them. It wasn't just a building block, it was a statement. In a world where many civilizations built with materials that would eventually return to the earth, the Romans were obsessed with building for eternity. Their concrete was the physical manifestation of that ambition, a direct expression of Roman identity and imperial power. Think about the materials other great cultures used. The Greeks built with beautiful but ultimately fragile marble. The Egyptians used massive stones, but their construction was limited by the size of the blocks they could quarry and move. Roman concrete liberated them from these constraints. With it, they could mold space itself. They could create the vast, soaring interior of the Pantheon, the staggering, multi-level complexity of the Colosseum, and the gravity-defying arcades of their aqueducts. This wasn't just about building bigger, it was about creating a new architectural language of arches, vaults, and domes that was uniquely and unmistakably Roman. It allowed them to shape the environment on a scale that had never been seen before, imposing their will on the landscape in a way that said, "We are here and we are permanent." This desire for permanence was deeply tied to their concept of empire. A kingdom built of wood and mud brick could fade away. An empire built of seemingly indestructible concrete would last forever. Every aqueduct that brought fresh water to a city, every harbor that secured a trade route, and every temple that awed its citizens was a testament to Roman power, order, and civilization. They weren't just building infrastructure, they were building a legacy. The concrete itself, with its slow, patient strength, mirrored the values they wanted to project: steadfast, enduring, and unbreakable. It was the perfect material for a people who believed their civilization was the pinnacle of human achievement and destined to rule the world forever. In the end, their empire did fade, but the concrete shells they left behind stand as a haunting and powerful reminder of that incredible ambition. a ghostly echo of a world they built to last. The reconstruction experiments, mixing ancient recipes today. How do we know all this? How can we be sure the recipe actually works? The final piece of the puzzle comes from modern builders and researchers who have done something incredible. They've rolled up their sleeves and tried to mix Roman concrete exactly as the ancients did. These reconstruction experiments are like a form of historical time travel, putting textbook theories to the ultimate test. The process is surprisingly physical and messy. It starts with slaking lime, which means taking quicklime, rocks of calcium oxide, and carefully adding water. This isn't a gentle stir, it's a violent boiling reaction that releases intense heat. Once the lime paste is ready, it's mixed by hand with the volcanic ash and aggregates, just as Roman laborers would have done. There are no modern concrete trucks or power tools. The goal is to replicate the entire system, not just the ingredients. The results are fascinating. The Roman mix feels different, thicker and more clay-like than modern concrete. It sets more slowly, and initial strength tests show it's not as strong as Portland cement after just a few weeks. But that's the whole point. The researchers then subject their samples to the real test. Time and the elements, they submerge blocks in seawater tanks and monitor them for years, watching for the slow, crystalline growth that Professor Jackson's research predicted. These experiments prove that the ancient methods weren't just folklore. They were a sophisticated, repeatable technology that we are only now relearning through hands-on, gritty work. The digital reconstruction modeling ancient chemistry. But you can't always wait centuries to see how a concrete mix will turn out. This is where modern technology offers a shortcut through time. Scientists are now using powerful computer simulations to digitally reconstruct the ancient chemistry, allowing them to peer into the future of a concrete recipe in a matter of hours instead of millennia. This digital alchemy lets them model the long-term molecular dance between lime, volcanic ash, and water, predicting how different combinations will behave over decades or even centuries. These computational models are incredibly complex. They simulate how ions dissolve, how they move through the microscopic pores of the concrete, and how they eventually combine to form new stable minerals. Researchers can input different variables: the exact chemical composition of the ash, the ratio of lime, the pH of the water, even the ambient temperature. Then they can fast forward the simulation to see which combinations are most likely to produce that coveted, stable, aluminous Tobermorite. It's like having a virtual time machine for material science. This digital testing ground is invaluable. It allows scientists to test thousands of hypothetical Roman recipes using modern, locally available pozzolans without ever having to physically mix a single batch. They can virtually test ash from a volcano in Oregon against ash from a mine in Germany, identifying which modern materials have the right geochemical signature to come closest to the ancient ideal. This isn't just about understanding the past, it's about building a bridge to the future. By using computers to do the initial heavy lifting, researchers can identify the most promising candidate recipes to then test in the real world, dramatically accelerating the process of bringing this ancient wisdom back to life. It's a perfect fusion of cutting-edge technology and timeless knowledge, using the power of the digital age to finally decode the secrets of the ancient world.